Hello and welcome to lecture 27 of our Essentials of Semiconductor Device Physics course. In this lecture, we begin a sequence of 3 videos where we're going to show a more mathematical analysis of the p-n junction in equilibrium. Okay, so last time we discussed qualitatively what happens when a p semiconductor is joined to an n semiconductor forming a p-n junction. We noticed that this is the same physics we discussed in lecture 9, but now with the inclusion of holes as also playing a role in the dynamics of the system. But we still have the same condition that we discussed in lecture 9 for currents, but now this condition for currents must be applied to both holes and electrons separately. And we also have the condition where that the Fermi level has to be constant across the semiconductor. This is shown here in the band structure. And recall that this happens because there is the creation of this electric field. So there is an associated electrostatic potential difference, which compensates the initial chemical potential difference in such a way that the Fermi level, which is the total potential, it is the electrochemical potential, is constant across the junction. And this time we're going to prove this identity, which connects the diffusion coefficient with the mobility. We're going to introduce this parameter, the mobility, in this lecture. And then we're going to use this identity in the next lecture to prove rigorously this equality, which we already expect to be true from the condition of equilibrium as we discussed in the previous lecture and in the lecture 9. So to prove both this identity and this identity, we're going to use the condition that the net flux in equilibrium is 0. But instead of using the flux in terms of the total current, we're going to use it in terms of the current density. So recall that the current density is the total current divided by the cross-sectional area. So imagine that the p-n junction is like a wafer. In this drawing here, we are showing this face. So the cross-sectional area would be this face here. So the total current is the current density times this area. And from now on, we're going to use the current density. And we also need, in future lectures, to define a reference parameter, which is the Fermi level of an intrinsic semiconductor. So we are not dealing with intrinsic semiconductors, but we can still speak of the Fermi level of an intrinsic semiconductor as just a reference value that lies in the middle of the band gap, like in an intrinsic semiconductor. So we're going to use this blue line, which by definition lies in the middle of the band gap, and we're going to use the expressions for the concentrations of N and P in terms of the Fermi level of an intrinsic semiconductor, using this blue line then as a reference. So this blue line you can understand as just being a reference value, and it corresponds to the Fermi level of an intrinsic semiconductor. But we don't have an intrinsic semiconductor. The physical Fermi level is represented by the dashed line. Okay, so we need now to recall some results we derived in previous lectures. So this is the condition of equilibrium, and we need the expressions for the drift and the diffusion current. So in lecture 13, we derived this expression for the drift current, and in lecture 16, we saw that the concentration of charge, when we are talking about electrons, is given by the concentration of electrons times the charge of an electron. So in this sense, the drift current for electrons is given by this expression, where we just replace the concentration here in here. So notice that we're going to use in this lecture this condition here when applied to electrons. We could do the same thing using the condition for holes. We would end up with the same result. So we can prove this identity either using electrons or holes, and I chose to use electrons. Okay, so now we need to use Ohm's law. We have not discussed Ohm's law in this course, but you may have already encountered it in other courses like electrostatics or electrodynamics. But all we need in this course is really the statement of Ohm's law. So according to Ohm's law, the drift current density is proportional to the electric field, and this proportionality constant is called the conductivity. So this is the conductivity of the material. So we want to recast Ohm's law in terms of the average velocity. So to do that, we can use this expression here for the drift current. So that's what we've done here. Then we can use this expression for the concentration of charge. That's what we've done in this line. And then we can solve for the average velocity, and we get this expression. So in this form, Ohm's law states that the average velocity is proportional to the electric field, and the proportionality constant, which is this term, is what we call the mobility, and we use the symbol mu for the mobility. And notice that the average velocity is antiparallel to the electric field. So if the electric field points to the left, the drift is to the right, because the force is in the other direction of the electric field, because electrons have negative charge. So this negative sign here comes from here, which is due to the negative charge of an electron. So we're going to use this form here of Ohm's law from now on. So that's our form we're going to use, and we're going to use it to express the drift current explicitly in terms of the electric field. So to do that, we use this expression here. So this negative sign cancels this negative sign, and we end up with this expression for the drift current, which we will use from now on. Now we need to recall the expression for the diffusion current. So in lecture 15, we derived this expression for the diffusion current, and when you use the concentration of charge in terms of the concentration of electrons, free electrons, then we can express this diffusion current explicitly in terms of the variation in the concentration of free electrons. So we went from here to here using this expression for the concentration of free electrons. Okay, so now we express the equilibrium condition that the net flux is zero in terms of the new expressions for the drift and diffusion current that we just found. So this term is the drift current, this term is the diffusion current. So this equality here is just this equality explicitly in terms of the electric field and the concentration of free electrons. So we end up with this expression, and then we can recast it in this form here by moving this term to the other side and by canceling the fundamental charge. And we also need the expression we derived in lecture 25 for the concentration of free electrons in terms of the energy level. So this is the Fermi level, it's this line, and this is the intrinsic Fermi level, so it's the blue line. That's why I left it in blue here, to emphasize that this term refers to the blue line and this term refers to the dashed line. So now let's evaluate this derivative using this expression for the concentration of free electrons. So notice that in this expression here, the only term that depends on space must be the Fermi level of the intrinsic semiconductor. This is the concentration of charge in an intrinsic semiconductor, so it does not depend on space. This is just a number. Once we decided the material and the temperature, this number is defined, and we already learned how to calculate it in the previous lectures. The temperature is fixed across the junction. The Fermi level of the junction, the physical Fermi level, is constant across the junction, so it cannot depend on space. This is exactly the condition of equilibrium. So this term cannot depend on space, otherwise the system is not in equilibrium. But the Fermi level of the intrinsic semiconductor, which is in the middle of the band gap, that will depend on space because the bands bend. So due to the band bending, we have that this term depends on space. So since this is the only term that depends on space, the derivative of the concentration of free electrons with respect to space can be conveniently expressed in terms of the derivative of the Fermi level of the intrinsic semiconductor with respect to space using the chain rule. So this is just the application of the chain rule for n. Now we can evaluate this derivative here explicitly. So it's just the derivative of n with respect to this term. So we end up with this expression. We have the negative sign here. Because of this negative sign, I have to divide by kBt because of this term. Now we recognize that the numerator here is just the concentration of free electrons, so it becomes this term. So we end up with this expression for the derivative, and then we can use it here to get this expression for the derivative of n with respect to x. And when you use this expression here, we end up with this equality connecting n, the concentration, the electric field, and the derivative of the intrinsic Fermi level with respect to space. Okay, so now we need to connect this term with the electric field. Recall that the only reason why the Fermi level of the intrinsic semiconductor, the blue line, depends on space is due to the band bending, and it's the electric field that causes the band bending. Remember that the band bending is due to the electrostatic potential difference associated with this electric field. So these two terms are not independent. Now we need to connect them explicitly to prove the equality that we need. So to do this, we just need to recall the meaning of the bending. Remember that this is the work done by the electric field. And this is only an application of the general relationship between a conservative force and a potential that we learned in mechanics. So recall that if we have a force, a conservative force, the work done by the negative of the work done by the conservative force gives the potential, the associated potential difference. In other words, the derivative of the potential with respect to space gives the force. So this is a very well-known relation in mechanics, and this is exactly this relation that connects this term, because this is the potential, with the electric field, which is causing the force. Okay, so then if we specify that this force is caused by the electric field, then we know that the force is given by the electric field times the charge of an electron. So this is the relationship that we know from electrostatics. And the variation of the Fermi level, so if I take the Fermi level in one point and subtract with the same Fermi level in another point near it, this variation is the work done by this force. So this equality here is exactly the same as this for the particular case that we are analyzing here. So our potential now is the intrinsic Fermi level. It's just a reference. But what matters is the variation. So we could have used here, for example, the bottom of the conduction band. We could have used the top of the valence band. We would get the same relation because the variation is the same for all energy levels. And when you express this force in terms of the electric field, we get this expression connecting the Fermi level of the intrinsic semiconductor with the electric field. And of course, we can recast this expression in terms of the derivative of the intrinsic Fermi level with respect to space, and we get this identity here, and we can use then this relation here, and we get this expression now where the electric field appears on both sides. Then we can just simplify this relation. The n here can be cancelled, and the electric field can be cancelled. Then we have that the mobility is given by the diffusion coefficient times the fundamental charge divided by kBt, which is exactly what we set out to prove. So if we move this part over here, we get this expression. So now we have proved what we wanted to prove, and in the next lecture we're going to use that identity to prove this relation that connects the electrostatic potential difference with the initial chemical potential difference. So we already know that this must be true from the condition of equilibrium, but in the next lecture we're going to prove that this is indeed true, invoking again the equilibrium condition for the currents, that the net flux has to be zero. So I see you next time.